Okay, thank you very much for the invitation. It's a real pleasure to give this talk. I'm sorry I have not been able to travel, but well, things are not so smooth these days. So, well, let's hope for that next week. Next time, I mean, it will be there. Okay, so I'm going to start talking about invariants of general algebras. This is a joint work with Cristian Chaparro from Colombia, Sibylle Schroll from Germany, and Mariano Suarez-Alvarez, who is also in Buenos Aires. And we have been working on homological invariants of general algebras for quite a long time now, but we are still adding new results about homology at this moment. And so I hope that in some short time we will finish and publish it once for all. Okay, so let me describe the objects and the problem. As I said, it's Hawkshield homology and cohomology of general algebras. These are the invariants, the homological invariants that I'm going to consider. And I'm not, I will just describe bases for Hawkshield cohomology and maybe homology, but I don't think I will have time for that. Because I want to concentrate in the algebraic structure of Hawkshield cohomology, which is given by the cup product. So the cup product makes HH of an algebra, a K-algebra A. It's a graded commutative ring with respect to the cup product that we are going to denote like this. Then the cap product that we are going to denote like this. And this gives the homology structure of a model over cohomology. And then finally, I would like to mention also the Gerstenhaber bracket. The Gerstenhaber bracket, they make, well, the Gerstenhaber bracket, let me write that if you have Hochschild cohomology for K algebra, general K algebra A in degree n, and then you have something in degree r of the same algebra, then with the bracket, you're going to end up having something in Hochschild cohomology in degree n plus r minus 1 of A, okay? So the Hochschild cohomology together with the Gerstenhaber bracket is a Lie algebra if we switch the degree with by 1. So all this structure together with, let me write it here. So together a differential of degree plus 1 that is usually called capital B from Hochschild homology to Hochschild homology then in degree plus 1. All this together satisfying some conditions is what is called a Tamarkin-Sigan calculus. So we describe all this structure for the Hochschild cohomology of general algebras. And why general algebras? Well, because on the one side, it's a family of algebras for which we can give a lot of details on the basis of the cohomology and the computations, and we can perform all computations, but they are also related to string theory in physics, in theoretical physics. They also have geometric models related to triangulation surface, and they are also related with algebras given by potential, a quiver with potential. So they are interesting from the computational point of view, and they are also interesting because they appear in many interesting places. So let me briefly give or recall the definition of a general algebra. So we are going to say that an algebra A is always going to be a K algebra over field K, and it is going to be gentle or then I will give a condition for finite dimensional Schendel, if and only if the algebra is Morita equivalent to a quotient of equivalent algebra divided by an ideal, where, well, there are some conditions. So any vertex, called the vertex B in Q0, vertex of the quiver, is the source of at most 2 arrows, the target of at most 2 arrows. So locally, things are like this. You can have 2 arrows arriving and 2 arrows going out, or maybe just one, or maybe just one arriving, or just like this, etc., etc. Okay? And the second condition is such that if, let me write it differently, if you have an arrow, an element in the quiver in degree 1, there exists at most 1 arrow E in Q1, such that AB is not in the ideal in the definition, and at most, same condition on the other side, so at most arrow, such that CA does not belong to the ideal, okay? If you have these conditions and moreover, the ideal I can be generated by monomials, then in this case, the algebra A is called string. But then we keep on adding some conditions. And the other condition is, again, on the arrows. It says that if you have an arrow in Q1, then there exists at most 1 arrow in Q1, such that AB belongs to the ideal. And similarly, on the other side, there exists at most 1 arrow C in Q1, such that CA is in the ideal. Okay? And the last condition, in order to be called a Schendel algebra, is that I can be generated by path of length 2, path of length 2. So it is quadratic. So in this case, the algebra is called Schendel. Okay? So moreover, if the algebra is finite dimensional, so if the ideal I is admissible, then for some n it is containing the power n of the radical, then it is going to be called finite dimensional Schendel. But then just to give some examples, we can have, for example, configurations like this locally. But then, for example, if you consider this arrow A, then you need to have one relation. You can continue in a non-zero way, just following one of the other arrows, okay? So maybe you have a relation here, and then you have this arrow A prime, and then maybe they have a relation here. So let's call this B and this C. Okay, so BA is 0 and CA prime is 0. But you cannot say that BA prime is 0, because then both CA prime and BA prime are going to be 0, and this is not allowed. Okay, so with each arrow, you can continue just in one way, which is non-zero. And just for this talk, let me suppose that the characteristic of the field is not 2, because if not, we know how to do it, but we have to consider many special cases, okay? So for the sake of the talk, we are going to consider a field with characteristics different from 2. So let me talk a little bit about Hawkshield, again, about Hawkshield cohomology of a K-algebra. So as I said, with the cap product, it is a graded commutative K-algebra, because first of all, it is a graded K-vector space. And then with the Gerstenhaber bracket, is a graded Lie algebra. We have to shift by 1, okay? But an interesting thing, I'm not going to define the Gerstenhaber bracket because it's very technical, but if you prefer geometry, then algebra, then you have to think that the Gerstenhaber bracket is the algebraic version, the Schouten-Neuhaus bracket, the Schouten-Neuhaus bracket. And they coincide. The algebra, well, nothing to do with the gentle algebra, but it's the algebra of C-infinity functions on a manifold, smooth manifold. So this gives you an idea of what more or less is the Gerstenhaber bracket. Okay, now let me recall some well-known results about the things that are known for Hochschild cohomology of I have not written it, sorry, it's here, but it's of gentle K algebra, not here. Okay, what I was saying was in general, but this is here for a gentle. Okay, then Sefilat-Kani computed without any proof, I must say, the dimensions, all the Hawkshield cohomology spaces for a gentle. And then Maria Julia Redondo and Lucrecia Roman also computed these dimensions, but they gave proofs, and they also gave some criteria for having zero cap product or Gerstenhaber bracket in some degrees, homological degrees. Okay, and then Yadira Valdivieso computed Hawkshield cohomology for a Jacobian algebra given by a quiver and a potential, and she gave a geometric interpretation, the dimensions. Okay, so this is related to triangulations of surfaces. So, well, one usual problem is how to compute the Gerstenhaber algebra structure. And when I say the Gerstenhaber algebra structure, I'm speaking about everything together, meaning the cap product, the Gerstenhaber bracket, and the fact that the Gerstenhaber bracket is graded by derivation with respect to the cap product. And why it is a bit complicated to compute this Gerstenhaber algebra structure? Well, because both the cap product and the Gerstenhaber bracket are originally defined in terms of the standard resolution, of the bar resolution of the algebra, resolution that Hochschild gave for Hochschild homology and cohomology. The problem is that we almost never use this resolution to actually compute the Hochschild cohomology. It is almost never to do actual computations. So we have the cohomology computed in some way, and we have the definition that is needed to compute Hochschild, cap product and the Gerstenhaber bracket in with a completely different resolution. So we need some results to change the resolution, but well, for the cap product, known, it has been known for quite a number of years yet, that if you have a diagonal from the resolution you use to compute the cohomology into the resolution times itself over the algebra, then you can use, it is possible to use the resolution R to compute the cap product. And this is what we do. Okay, we define a diagonal that I'm going to mention later. But for the Gerstenhaber bracket, well, it has been a quite open problem till some years ago, and there have been some recent results, I mean the last 5 years, on this subject that are mainly given by Chris Negron, Sarah Witherspoon, on one side, and by Mariano, Suarez-Alvarez. But, well, for the first method, the thing is that one needs to compute a certain homotopy, so it mainly works, for example, Koszul algebra. Here we are able to use it because general algebras are Koszul algebras, usual Koszul algebras. Okay, and then the method by Suarez-Alvarez is easier, but the problem is that it is just possible to use it in order to compute the brackets of an element of H1 with an element in any cohomological degree. And we obtain something in Hn minus 1. Okay, so in our work, we have combined we have combined both approaches, and in order to make things easier. Okay, so the first thing we need in order to give all the structure is a description of the Hawkshield cohomology as a vector space, okay, as a graded vector space. And for this, we are going to give bases. And I am trying to explain what the bases, what these bases mean in a kind of geometric way related to the quiver and the relations of the algebra. Okay, so I'm going to give the result for cohomological degree 0, and then degree 1, and then for higher degrees. Okay, so what do we have in degree 0? Okay, so let's start with an algebra like this. Let me introduce a bit of notation. So the notation I'm going to introduce here is that gamma and alpha are always going to denote path in the quiver Q. And when I write a pair like this, gamma alpha, it means that gamma is parallel to alpha, meaning that gamma is a path, for example, here, and alpha is another path, or maybe the same, and they start and end at the same point. So I mean this when I say gamma is parallel to alpha, okay? And then we are asking gamma to be in a set that is called gamma I, that appears in the resolution, in the minimal resolution of the algebra. And the thing is that in order to be, for example, in gamma 2, it means that you have 2 arrows and there is a relation between the 2 arrows. And if gamma is in gamma 3, then you will have 3 arrows and relations, the superposition of relations like this, okay? So in gamma I, you have superpositions of I minus 1 relations. But so of course, gamma is going to be 0 in the algebra, but it's used for the resolution. And then the parallel path alpha is not 0 in the algebra, so it's part of the basis, and it has, when I write Bn, is something that is in the basis and has length equal to n. Okay, so this is for the notation. Well, in degree 0, there is always, absolutely always, this element, this first element here, which is the identity, okay? The identity of the cohomology ring, okay? So this is the identity of the cohomology ring. And it means that you have for each vertex E, well, you consider the path that is E parallel to E, okay, it's of length 0, and they satisfied by definition these conditions. And then you add them. And this is because H0 is the center of the algebra, so this element is going to be in the center of the algebra. There is a second type of elements, which is the following one. So we are considering a pair. Alpha is a path that is not 0 in the algebra, suppose like this. And suppose that here S of alpha is the source of alpha, where it starts. So here we have alpha. Alpha is invariant, it is not 0. And the valency of the vertex source of alpha is 2, meaning the valency is the sum of the number of arrows ending source of alpha plus the number of arrows starting source of alpha. So here the local configuration is just like this. You have one that is the last one in alpha that is arriving and one that is continuing. And then you ask alpha to be maximal in B, meaning that you cannot continue in a non-zero way. So here there has to be a relation between the last arrow of alpha and the first one. Okay, so this kind of configurations in the quiver with this relation give an element in the basis of HH0. And then we have another kind of element which appears only in the infinite dimensional case for A. Oh, and this element is, well, here we are going to consider alpha, where alpha here is the primitive cycle, meaning that it's not a power of a shorter cycle. And then we suppose that it has period R, and then you can rotate it in all the possible ways. And we are going to consider this, the source, which is in Q0 for each rotation, and then the rotated cycle, which has some length, okay? And the cycle alpha is in B, but we also ask alpha squared to be in B. So here is the infinite dimensional case because we have a configuration, for example, like this, but we do not need to have a relation here as before. Okay, so this is not needed. Okay, in fact, it is not there. And the valency, well, it can be greater than 2. Okay, so this only appears in the infinite dimensional case. And then for the basis of HH1, let me go a little bit faster. We have a kind of 2 configurations that are called shortcuts and deviations. And the shortcuts, you have an arrow A, which is parallel to a path of some length. The path is not 0. A never appears in the generators of the ideal. A is maximal, is gamma maximal, gamma meaning with respect to relations. So if, for example, there is an arrow going out here, then you're never going to have a relation between 2 arrows. And the same for arrows arriving to the source of A. And A and alpha, they do not share arrows, meaning that A is not appearing in alpha. And then another type of configuration where we consider the arrow parallel to the path that is going through alpha 1, which does not start with A, then A, and then alpha 2, which does not end with A, okay? And the lengths of both alpha 1 and alpha 2 are positive, okay? So here we are calling this a deviation. There are some more conditions, is that as before, A does not appear in the generators of the ideal. It is gamma maximal as before, and as I said, they do not start neither end nor end with the same arrow, okay? So these are elements of more or less the same type, and in the interesting thing for describing the cohomology in this way is that we can see it from the quiver. We look at the quiver and the relations, and we are immediately able to describe the Hawkshield cohomology. And then 2 more types of elements. One is the following. So suppose that we consider the arrows, Q1, and we take out T, which is the maximal tree. For example, let me do it here. We have, suppose that we have these arrows in the underlying graph. Okay, so here, for example, in order we can consider the maximal tree, for example, this one. Okay, so we are going to have for this set of elements an arrow A here that is in the complement of a maximal tree. Okay, of course, we can choose a maximal tree in several different ways, but of course the elements in the basis of the cohomology in degree 1 are going to change, but they are going to be isomorphic. The result we obtain, they are going to be isomorphic. And then again, there is a set of elements that appear only in the infinite dimensional case. So for infinite dimensional A, that are related with cycles again. So let's consider delta a cycle such that the square is in the basis, it's not zero in the algebra, and so delta is not zero in the algebra. And then a circuit, well, is the set obtaining by rotating it in all possible ways. And then for this set, we pick a representative. So it's a representative of a circuit, okay? And then we pick the representative and we have elements like this. So it's kind of having, let me call it delta here. And then you continue once more with C. So you get something that is the arrow, which is parallel to all this, okay? So C is the first arrow of the representative that has been chosen. So please, if you have any questions, don't hesitate to interrupt me. And then this is for degree 1. So as you see, it can be really described in the graph. In higher degrees, well, there are less types of elements. So we are describing here the basis for HHM with m greater or equal to 2. And we have some sums that consist of cycles, rotations of cycles C that are full of relations. They have period R, and this is indexed in the sum. There is a sign, and then we consider all the possible rotations of C, and the second element, which is in the basis, is just the source of the cycle that we are considering in each term, okay? And then for each cycle as before, but in degree 1 less, we can, as before, continue it with one arrow, but it is full of relations, okay? So this is the description of the Hawkshield cohomology, okay? And there is one more element, okay? But this element is of the same type as the shortcuts and the deviations we had before, because it's a gamma parallel to alpha. Gamma is full of relations, okay? Every composition of two arrows is 0. Alpha, and the contrary is in the basis, they are parallel, and they do not share neither the first nor the last arrow, okay? And this is, as I said, an element of the same type of the shortcuts and the deviation. A first corollary that we can obtain from this description is the following. And well, let me briefly give an idea of the proof of this corollary. So suppose that we have a finite dimensional general algebra with a presentation given by equivalent relations. Then if we consider the set of all the dimensions of the cohomology spaces, well, this set is bounded. And we can give a more precise bound, so we call capital N the number of primitive is not the power of another cycle, complete, meaning that all the compositions of two arrows is 0 in the algebra, well, cycles in the quiver. then the dimension of HHM for all M that is bigger than the number of arrows in the quiver is going to be smaller or equal to 2 times this number, capital N. And moreover, if we are in cohomological degree that is bigger than the number of arrows, then the cohomology, and we have that the cohomology is different from 0, then we will have infinitely many integers such that the cohomology in the corresponding degree is different from 0. Okay, so let me give an idea of the proof. So the first part of the proof. Let us consider the number of gamma maximal path primitive. Okay, they are not the power of another gamma maxima of another path. So this number is finite. They all have at most the number of arrows. So why is this? Well, indeed, if the length of a path is bigger than the number of arrows, then there is at least one arrow appearing twice. And if it belongs to gamma, the path, it cannot be gamma maximal, because you're going to continue going around and you will continue having relations. So because you already have more than one, you have been going around the cycle more than once, okay? So from this, it's just counting, it follows, it's bigger than the number of arrows, then the cohomology in degree M is freely spanned, because we have the basis, the following elements, the vector space spanned by what the resolution has in degree M parallel to the basis. So as we have seen before, we have the sums of this type that I'm not going to write again, but C is a representative of a path full of relations. And then for the shorter, one less, length one less, we have this type of elements. So here C is a representative of a complete cycle of degree 1 less, okay? So thus, such an M, we have that the dimension of the K-vector space of HHM is smaller or equal than the number of elements in the first case, plus the number of elements in the second set, okay? And each of them is smaller or equal to n, okay? And this is because primitive cycles are disjoint rotations of the same. So from here, we obtain the 2n that we had in the degree, okay? So, well, I'm not going to give the proof for the second part because, I do not have time, but just a remark is that under these conditions, if Cm, the representatives, is different from the empty set, then for all k is also going to be non-empty, okay? Because we can turn around once and again, okay? So let me, in the 5 minutes I have left, let me mention about the cup product. So we have used a diagonal map here for the Basel resolution, which is the minimal resolution for a monomial algebra. And the formula is quite easy using this diagonal, because if we have a pair gamma parallel to alpha, and we do the cup product with gamma prime parallel to alpha prime, both of them in the basis of the cohomology, then either we just compose, if for example the terminus of gamma prime is the source of gamma, and there is a relation continuing them. And we also compose alpha and alpha prime, which are parallel. And so if if gamma gamma prime belongs to the corresponding set in the resolution, and the terminus of gamma prime is the source of gamma, and 0 if not. So it's quite easy as a formula. And then, as a consequence, we obtain the generators of the Hawkshield cohomology as an algebra. We can describe them. Considering the generators that we have shown, well, they are this set that is listed here is minimal, except in one case, that is when the quiver has just one vertex and one arrow, one loop, okay? Because, well, if we skip the case in characteristic 2, well, we consider also when A squared is not the ideal, meaning that the dimension of the algebra KQ over I here is infinite, okay? And why it is not minimal, the set in this case? Well, because then if you do the cap product of the source of A, which is the only vertex parallel to A, with A parallel to the source of A, what you obtain is the pair A parallel to A, which is also listed, well, here. And well, of course, it is in the complement of a maximal tree. Okay, so if we exclude this case, then the set is going to be minimal. We get, well, a lemma describing the graded Jacobson radical of the Hochschild cohomology. But what is most interesting from this lemma is the corollary, the first corollary, for example, saying that if, as before, we consider capital N the number of cycles full of relations, okay, primitive ones, then the Hochschild cohomology modulo the radical is going to be graded commutative, no? It's going to be a quotient of a polynomial algebra in exactly capital N variables divided by all the products of different indices, okay? So in particular, this number N, which counts complete cycles, is a derived invariant of the algebra, okay? So it's always useful to obtain derived invariants of the algebra that can be recovered from the quiver, okay? And this mostly use the structure of the Hochschild cohomology in degree 0, but if we want to obtain more invariants that are really cohomological invariants, then we have to consider this finite dimensional graded vector space, that is the radical quotient, the radical square. So we consider it Hilbert-Poincaré polynomial, defined as usual like this. Well, it is also a derived invariant. So all the dimensions of the homogeneous components of this graded vector space are cohomological invariant, so are derived invariants. And why this happens? Well, this happens because all these numbers can be computed from the Hochschild cohomology spaces, okay? So this is the end of my time and of the talk. And my idea was to expose how to obtain invariants, graphical invariants or numerical invariants from the computations of the computation of a cohomology. So thank you very much for your attention, and I hope it has been clear.
Any question from people in person or on the, yeah, Kavi, open your microphone simply.
Well, thanks for the nice talk. I have, in fact, two questions, one of which is probably a very naive question that you must have already answered, is what are your obstructions when you want to generalize these results from gentle algebras to string algebras? You're still working with monomial relations, but not necessarily quadratic. So what are the abstractions over there?
In fact, there are more abstractions to generalize this to string algebra, which nevertheless we are trying to do now. But there are almost no abstractions to generalize this to quadratic monomial algebras. Okay, we in fact are able to do at this point all the computations for a quadratic monomial. For string algebras, the problem is that, well, of course, you can have, there are still monomial, as you say, but you can have relations that are longer, okay?
Yep.
So when you have superpositions that appear in Barsa's resolution, then you cannot manage working with them so well. So for example, for the cup product, then you will have holes and you will have to deal with it. So for example, here, for the cup product, let me just mention, the diagonal, let me write the diagonal. The diagonal is quite easy because if you have, for example, an element which is, well, Cm, let's say C1, that appears in the Barsa resolution. So here, what do you have? You have M arrows, and all these compositions are 0. Okay, and then you just send it to all the possible ways of splitting it. Okay, from 1 to M or M minus 1, and then you split it. Tensors, Cm, Ci, tensor 1, and then tensor over A, this is plus 1, tensor Ci up to C1. Okay, and you are sure that here and here you are elements that will appear in the resolution because they all have superpositions. Well, in the case of a string non-quadratic algebras, it's more difficult because there are terms that will never appear because they are not in the correct place in the resolution. And you have to be able to deal with it. So we are trying to do it, but for non-quadratic, we still don't know. We know how to do it in a concrete algebra, but we don't know how to do it in general.
We've run out of time, so I guess we'll thank Professor Solotar again.